When a patient logs into a telehealth visit, that single interaction depends on an enormous, fragile chain. The video relies on a home broadband link, which connects to a mobile carrier, which pings an identity service, hits hospital storage, and routes through an AI assistant. If any one of those links stalls, the entire service drops. The engineering flaw in this ecosystem is how we manage the individual parts. Compute, network, storage, and security systems each monitor their own health. They optimize for their localized metrics, entirely in isolation from one another. Because of this fragmentation, no single local controller possesses a complete end-to-end view of the actual outcome. The storage array doesn't know if the patient got their video feed, and the network doesn't know if the database successfully retrieved the health record. This diagram illustrates the problem operators face. Look at the left side, labeled Today. We have compute, network, storage, and security operating as disconnected silos. When a bottleneck occurs, administrators are forced to guess which box is actually causing the delay. You can allocate more GPU power or pay to increase network bandwidth. But if the hidden constraint is a stalled storage retrieval pathway, that extra capacity is wasted. You haven't fixed the problem, you've just moved the bottleneck. Automated systems operating on different timescales actively make this worse. A network controller might detect congestion and reroute traffic, while a security tool simultaneously notices the strange new traffic pattern and quarantines a host. They execute conflicting actions based on incomplete pictures. The rise of agentic AI is pushing this architecture past its breaking point. We are moving from chatbots to autonomous software that continuously calls tools and retrieves data over time, introducing unpredictable, prolonged load across the entire infrastructure chain. Current monitoring systems are entirely reactive. They fire off alerts and dashboards long after the user has already experienced the failure. Operators are left scrambling to reconstruct the disaster backward while the system is actively degrading. Modern reliability hinges on solving the coordination failures that local controllers are unable to see. Moving to the right side of the diagram, we see the proposed structural solution, the Predictive Tensor Control Plane, or PTCP. It is designed to act as a software overlay, sitting above the silos to observe the relationships between them. Notice the architectural constraint written at the bottom. PTCP is an air traffic coordinator, not a pilot. It does not replace the native hardware controllers on your servers or routers. Instead, it coordinates policy, risk, and priority across them. This forces a shift in how we measure success. Traditional quality of service asks a very narrow question. Did a specific packet of data receive priority on the network? Tensor Networks proposes a framework called AI quality of service. It requires measuring whether a useful, complete task finished within strict latency, cost, and security boundaries. To guarantee that a complex AI task finishes on time, operators need an intelligent overlay capable of predicting structural failures across the entire chain before they manifest as data loss. The engine driving this predictive capability is a modeling framework known as Tensor Network Quantum Gravity, or TNQG. Despite the name, this is not a quantum computer, nor is it a post-quantum cryptographic algorithm. It is a physics-inspired classical mathematical framework for analyzing complex geometry. It respects privacy by operating on payload minimal telemetry. Instead of reading the contents of your emails or databases, it ingests metadata, cues, timing, and reachability. Infrastructure produces far more telemetry than human operators can read. PTCP compresses that massive volume of data into a manageable tensor representation. By analyzing this data, it maps the system's normal patterns of life. Mapping this topology allows the system to calculate exact dependencies. It understands which users can reach which databases, and exactly how a small change in one server will propagate down the chain. It identifies the blast radius before the failure actually hits the user. In legacy operations, IT teams have to manually rebuild these dependency chains while fielding angry phone calls during an active outage. There are strict mathematical limits to this approach. Tensor compression reduces complexity only when the underlying data has a stable, recurring structure. It will not perfectly predict every chaotic, random workload. Forecasting infrastructure health relies on understanding the geometry and internal dependencies of the entire ecosystem.
This diagram illustrates how PTCP physically operates in an enterprise environment, splitting tasks into two distinct continuous loops. The first is the slow path, or planner. Operating from milliseconds to seconds, it gathers telemetry, learns normal patterns, and estimates the uncertainty of emerging risks. The slow path is also where PTCP rehearses. It tests candidate responses in a digital twin, confirming that a policy will work before it ever touches production hardware. Then we have the fast path, the guardrail. This operates right at the workload edge, using technologies like eBPF in the Linux kernel or edge gateways. The fast path does not brainstorm. It executes a strict, limited vocabulary of pre-authorized actions: rate limit, prioritize, isolate, or rollback. This separation is a strict requirement. PTCP cannot and should not attempt to remotely deliberate over every single packet or microsecond routing decision from a centralized server. Pushing enforcement down to the edge ensures that native systems retain total control over the immediate physics of their hardware. Safe infrastructure intelligence relies on this decoupling. You build a system with slow, heavy simulation in the control plane, paired with fast, lightweight, bounded enforcement at the edge. This flowchart details how the predictive data fabric is packaged into specific enterprise applications. Look at the AI factory. When an AI agent stalls retrieving data, PTCP detects the bottleneck. Instead of processors spinning uselessly, it dynamically defers low-value training to prioritize live retrieval. By reducing idle accelerator time and eliminating unnecessary retries, the operator drastically lowers the energy, the actual physical joules, and the cost required to generate each successful task. The framework applies to security as well, through the zero-day application and a concept called topological caging. Standard security tools often wait to inspect a payload to confirm malware, but if stolen credentials or a rogue AI agent begin traversing an abnormal dependency path, PTCP recognizes the structural deviation immediately. It restricts its reachability dynamically, locking down the pathways before the incident spreads. Across both power efficiency and cybersecurity, the ultimate operational value of a unified control plane is time. It buys time to save power during a compute surge and time for human responders to investigate a breach. This flowchart maps a central caveat. Technical optimization inside a data center does not automatically equal public civic value. The recovered capacity and energy savings must be actively passed through to the taxpayer, either by markets lowering prices or regulators requiring higher reliability. When that translation happens, digital efficiency becomes human safety across different societal sectors. During severe network congestion, PTCP recognizes an emergency imaging transfer has a critical deadline. It defers bulk backups to ensure the doctor receives the scan on time. During a regional disaster, the physical AI application preserves the freshness of emergency vehicle location data, actively dropping non-critical roadside video streams to keep the network clear for first responders. In these scenarios, the software does not make medical diagnoses, and it does not dispatch police. It purely preserves the digital conditions required for human professionals to execute their missions. Continuity of service under stress defines the success of public infrastructure. Granting a software overlay this level of visibility carries a primary risk: centralizing power. A highly capable control plane must never become an invisible system of unaccountable priority. Any change executed by PTCP requires bounded action. Operate under a published authority, a tightly defined scope, a strict expiration time, and an immutable evidence trail. Organizations cannot simply flip a switch to turn this on. Deployment requires mandatory, staged scale gates, progressing from observe-only telemetry mapping to shadow digital twins before ever attempting a live canary actuation on real traffic. Most importantly, public safety requires a critical architectural design rule: the declared fail mode. If the control plane is attacked or hallucinates, local infrastructure must immediately sever ties and revert to its native baseline safety rules. The local hardware always takes back control. No software overlay can fix weak hardware, or repair a snapped fiber cable, or guarantee that an agency's underlying policies are fair. Equipping these systems with shared memory and foresight ensures they remain safely under human purpose when the pressure is highest.